Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silbershatz, Greg Gagne, and Peter Galvin. Published by Wiley Publishing. Last two lessons we have been discussing about deadlock, and in this lesson we're going to address a few of the methods for handling deadlock. So let's begin. We can deal with the problem of deadlock in one of three ways. We can ignore the problem altogether. We can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlock state. Or we can allow the system to enter a deadlock state, detect it, and recover. The first solution is one used by most operating systems, including Linux and Windows. It is then up to the kernel and application developers to write programs that handle deadlock, typically using approaches outlined in the second solution, developing protocols to prevent or avoid. Some systems, such as databases, adopt a third solution, which is to allow deadlocks to occur and then managing the recovery. Some researchers have argued that none of the basic approaches alone is appropriate for the entire spectrum of resource allocation problems in operating systems. The basic approaches can be combined, however, allowing us to select an optimal approach for each class of resources in a system. To ensure that deadlocks never occur, the system can use either a deadlock prevention or a deadlock avoidance scheme. Deadlock prevention provides a set of methods to ensure that at least one necessary conditions we discussed earlier, mutual exclusion, hold and wait, no preemption, or circular wait, cannot hold. These methods prevent deadlocks by constraining how requests for resources can be made. Deadlock avoidance requires that the operating system be given additional information in advance concerning which resources a process will request and use during its lifetime. With this additional knowledge, the operating system can decide for each request whether the thread should wait. To decide whether the current request can be satisfied or must be delayed, the system must consider the resources currently available, the resources currently allocated to each process, and the future requests and releases of each process. If a system does not use either a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may arise. In this environment, the system can provide an algorithm that examines the state of the system to determine whether a deadlock has occurred, and an algorithm to recover from the deadlock. In the absence of algorithms to detect and recover from deadlocks, we may arrive at a situation in which the system is in a deadlock state and has no way of recognizing what has happened. In this case, the undetected deadlock will cause the system's performance to deteriorate because resources are being held by threads that cannot run, and because more and more threads, as they make requests for resources, will enter a deadlock state. Eventually, the system will stop functioning and will need to be restarted manually. Although this method may not seem to be a viable approach to the deadlock problem, it is nevertheless used by most operating systems, as I told you earlier. Expense is one important consideration. Ignoring the possibility of deadlocks is cheaper than the other approaches. Since in many systems deadlocks occur infrequently, the extra expense of the other methods may not seem worthwhile. In addition, methods used to recover from other liveness conditions, such as live lock, may be used to recover from deadlock. In some circumstances, a system is suffering from a liveness failure but is not in a deadlock state. We can see this, for example, with a real-time thread running at the highest priority, or any thread running on a non-preemptive scheduler and never returning control to the operating system. The system must have manual recovery methods for such conditions and may simply use those techniques for deadlock recovery. As I just mentioned, for a deadlock to occur, each of those 4 necessary conditions must hold. That is, mutual exclusion, hold and wait, no preemption, and circular wait. By ensuring that at least one of these conditions cannot hold, we can prevent the occurrence of a deadlock. Let's elaborate on this approach by examining each of the 4 necessary conditions separately. The mutual exclusion condition must hold. That is, at least one resource must be non-shareable. Shareable resources don't require mutually exclusive access and therefore cannot be involved in a deadlock. Read-only files are a good example of a shareable resource. If several processes attempt to open a read-only file at the same time, they can be granted simultaneously access to the file. A process never needs to wait for a shareable resource. In general, however, we cannot prevent deadlocks by denying the mutually exclusive condition because some resources are intrinsically non-shareable. For example, a mutex lock simply cannot be shared by several processes. While a printer cannot be shared, it is possible to use a software approach called a spooler to give the sense that everyone is able to print at once. But that's another story. Now, to ensure that the hold and wait condition never occurs in the system, we must guarantee that whenever a process requests a resource, it does not hold any other resources. One protocol we can use requires that each process request and be allocated all its resources before it begins execution. This, of course, is not practical for most applications due to the dynamic nature of requesting resources. A process may request some resources and use them. Before it requests any other additional resources, it must first release all the resources that it is currently allocated. Both of these protocols have 2 main disadvantages. The first disadvantage is that resource utilization may be low, since resources may be allocated but unused for a long period of time. For example, a process may be allocated a mutex lock for its entire execution, yet only require that lock for a short period. The second disadvantage is that starvation is possible. A thread that needs several popular resources may have to wait indefinitely because at least one of the resources that it needs is allocated to some other thread. A thread that needs several popular resources may have to wait indefinitely because at least one of the resources that it needs is always allocated to some other thread. The third necessary condition for deadlocks is that there be no preemption of resources that have already been allocated. To ensure that this condition does not hold, we can use the following protocol. If a process is holding some resources and requests another resource that cannot be immediately allocated to it, that is, the process must wait, then all resources the process is currently holding are preempted. In other words, these resources are implicitly released. The preempted resources are added to the list of resources for which the process is waiting. The process will be restarted only when it can regain its old resources as well as the new ones that it is requesting. Alternatively, if a process requests some resources, we must first check whether they're available. If they are, we allocate them. If they are not, we check whether they are allocated to some other process that is waiting for additional resources. If so, we preempt the desired resources from the waiting process and allocate them to the requesting process. If the resources are neither available nor held by a waiting process, the requesting process has to wait. While it's waiting, some of its resources may be preempted, but only if another process requests them. A process can be restarted only when it has allocated the new resources it's requesting and recovers any resources that were preempted while it was waiting. This protocol is often applied to resources whose state can be easily saved and restored later, such as CPU registers and database transactions. it cannot generally be applied to such resources as mutex locks or semaphores, precisely the type of resources where deadlocks most commonly occur. The three options presented so far for deadlock prevention are generally impractical in most situations. However, the fourth and final condition for deadlock, the circular wait condition, presents an opportunity for a solution by preventing one of the necessary conditions. One way to ensure that this condition never holds is to impose a total ordering of all resource types and to require that each process request resources in an increasing order of enumeration. Let's say we have a set of resource types. We assign each resource type a unique integer number, which allows us to compare two resources and determine whether one precedes the other in ordering. We can accomplish this scheme in an application program by developing an ordering among all synchronization objects in the system. Keep in mind that developing an ordering or hierarchy does not in itself prevent deadlocks. It is up to the application developers to write programs that follow the ordering. However, establishing a lock ordering can be difficult, especially on a system with hundreds or even thousands of locks. It's also important to note that imposing a lock ordering does not guarantee deadlock prevention if locks can be acquired dynamically. The remaining sections of this chapter of your textbook delve more deeply into solutions like these, including methods of deadlock avoidance and recovery. However, for our purposes, this is as deep as I want to go into the discussion of deadlock. If you're interested in learning more, please refer to the additional material in the book and elsewhere. And that concludes Unit 8 of our course.